It's 8 a.m. I think we can start. Welcome, everyone. Welcome to the 23rd Climate Intervention Symposium. Our first speaker is Dr. Anna Lange from University of Greifswald. Anna, you can correct me if I pronounce everything wrong. And the floor is yours.
Perfect. Thank you for the introduction. And in the next few minutes, I give a quick overview of our results on the detectability of possible stratospheric aerosol injections with satellite solar occultation instruments. And in doing so, I talk about two aspects. First, about the detectability of stratospheric aerosols formed from continuous injections of 1 and 2 teragram sulfur per year from the perspective of a typical satellite solar occultation instrument. And in the second part, I talk about the so-called zero transmission problem in solar occultation measurements that can arise with large to larger scale SRI deployments. As everyone is probably aware, I'm talking about stratospheric aerosol injections. So number 3 here in this illustration, also called SRI. And SRI deployments above a certain size can probably be observed with solar occultation instrument, like for example, SAGE 3 ISS. SAGE 3 ISS is one of the currently active satellite solar occultation measurements that measures solar occultation instrument that measures the attenuation of solar radiation due to scattering and absorption of atmospheric components such as ozone, water vapor, and aerosols. So therefore, solar occultation instruments can probably be used to detect future SRI deployments above a certain size. So in the first part, I talk about the detectability of continuous injections of 1 and 2 teragram sulfur per year. And for that, we used Eckam-Ham model simulations performed von Ulrike Niemeyer. And we used these model simulations contain aerosol extinction coefficients for an altitude range of 10 to 27 kilometers. And for this purpose, sulfur dioxide was continuously injected into one grid box centered on the equator with 121 degrees east and an altitude of about 19 kilometers. We analyze the initial phase, meaning the first 2 years, and the quasi-steady state phase as an average over 3 years. And we also looked at a latitude range of 85 degrees north to 85 degrees south for the months of January and July. And with these aerosol extinction profiles, we calculated the corresponding transmission values from the perspective of a typical satellite solar occultation instrument using the radiative transfer model skiatran. And with these transmission values, calculated transmission values, we also, as an input with the transmission values, performed the stratospheric aerosol extinction profile retrieval also using skiatran. The retrieval approach here is the regularized inversion with the optimal estimation method. For more details on the methodology, I refer to our paper or the Q&A part later, but the basic idea is simply that the artificial aerosol enhancement is observable in a certain altitude range if the background profile is outside the error range of the retrieved aerosol extinction profiles of 1 and 2 teragram sulfur per year. The plots here show now the results for the quasi-steady state phase for the upper planets for 1 teragram sulfur per year, the lower planets for 2 teragram sulfur per year, left January and right July. Here exemplary shown for 65 degrees north, and the black solid line is the background profile, meaning no SRI, so 0 teragram sulfur per year. The black dashed line is the retrieved aerosol extinction profile with the corresponding total errors depicted here as the red dashed line. And in all cases here, exemplary shown for 65 degrees north, the background profiles are outside the error range of the retrieved aerosol extinction profile.
Could I ask a couple of questions, clarification? Are you emitting SO2 but you're quantifying as mass of sulfur.
Yeah. Okay.
And what latitude are you emitting it?
So it's a grid box centered on the equator, 2.8 degrees times 2.8 degrees.
Okay, thank you.
No problem. Okay. So this is also shown here for, again, the quasi-steady state phase, 1 teragram sulfur per year, and the lower peninsula 2 teragram sulfur per year, January and July. The SRD, so stratospheric aerosol operated depth over latitude, again, black solid line is the background case, and the black dashed line retrieved case with the corresponding total errors in red. And also here, the background profiles are outside the error range. So under the assumption material and conditions and constraints, the formed stratospheric aerosols formed from continuous injections of 1 and 2 teragrams sulfur per year can probably be detected with satellite solar occultation instrument for the quasi-steady state phase. But this is not the case for the first month of the initial phase, as shown here, again, SOD over latitude for 1 teragram sulfur per year, January, and as depicted here, the background profiles just for a specific latitude range outside the error range. But however, the natural variability has not been taken into account so far, and the SLD or the SI signal is considered detectable here if the corresponding SIOD values are outside the 2 sigma range of the natural variability here for nearly background conditions. And for the quasi-steady state phase with 1 and 2 teragrams sulfur per year, the corresponding SIOD values are outside the 2 sigma range of the natural variability. So meaning also on considering the natural variability, it is very likely that the formed stratospheric aerosols formed from continuous injections of 1 and 2 teragrams sulfur per year can probably be detected, but this is not the case for the first month of the initial phase, meaning in the first month of the initial phase, the signal of the emission of 1 teragram sulfur per year cannot be distinguished from the natural variability. To summarize the first part of my talk, so stratospheric aerosols formed from emissions of 1 and 2 teragram sulfur per year can probably be observed for the quasi-steady state phase under the conditions and constraints considered here. But this is not the case for the initial phase, since the signal of the emission of 1 teragram sulfur per year cannot be distinguished from the natural variability. And although 1 and 2 teragram sulfur per year do not have a significant climate effect, these emission rates were chosen to see whether it is possible to detect even these small amounts with a satellite solar occultation instrument. The second and last part of my talk is about the so-called zero transmission problem in solar occultation measurements that can arise with large to larger scale SRI deployments. And the methodology is nearly the same as described before, but here with 30 teragrams sulfur per year. Here an example for the aerosol extinction coefficients from Eckham-Ham at 550 nanometers, and the so-called zero transmission problem was already highlighted by the Mount Pinatubo eruption in 1991, which leads to measurement gaps in areas of high aerosol loadings due to the resulting low transmission from the perspective of the satellite solar occultation instrument. So consequently, it is highly unlikely that a physically meaningful retrieval result of the stratospheric aerosol extinction profile is possible depending on the latitude and wavelength. So the question here is, and also guiding the last part of my talk, is which wavelengths are required for plausible stratospheric aerosol extinction profile retrievals depending on the latitude, assuming continuous tropical emissions of 30 teragrams sulfur per year. Let's show here now retrieval results for a latitude of 5 degrees north if when the corresponding stratospheric aerosol extinction profile retrieval is performed at 520, 1543, 1800, and 1900 nanometers. And the blue line shows the retrieved aerosol extinction profile, and the orange one, the true profile, aerosol extinction profile, so the simulation results from ECHAM. And the results show that with increasing wavelength, the true profile, the retrieved profile gets closer to the true profile, so the blue line to the orange line, with the best agreement at 1900 nanometers. That means that, under the assumption made here, a wavelength of at least 1900 nanometers would be necessary for the retrieval for the latitude of 5 degrees north. This is also consistently shown here for the transmission comparison and the relative residuals, again for the latitude of 5 degrees north, the upper panel for 520 nanometers, the lower panels for 1900 nanometers, and the blue line are the simulated transmission values, so the transmission values from the perspective of a typical satellite solar occultation instrument based on the retrieved aerosol extinction profiles, and the black line is the so-called true transmission, so the calculated transmission values from the perspective of the typical satellite solar occultation instrument based on the so-called true profile, aerosol extinction profile, so the results from the Eckham-Hum simulations. And what is also shown here are the differences in the transmission values between the wavelengths. So for 5 to 20 nanometers, at the minimum transmission values at about 10 to the power of minus 14, and for larger wavelengths, so 1900 nanometers, transmission values in the minimum of about 10 to the power of minus 5. And what is also shown here and already concluded from before is the good agreement between the transmission values for 1900 nanometers with a maximum relative residuals of 1.4 for a Tonkin height of 22 kilometers. So although 520 nanometers are not sufficient for the latitude of 5 degrees north, a different conclusion can be drawn for 75 degrees south, panel A, and 75 degrees north, panel B. And again, here the blue line is the retrieved profile and the orange line is the true profile. And the transmission comparison is shown here for 75 degrees north. And as depicted here, there's a good agreement between the retrieved and the true profile for 520 nanometers. We did that also for 45 degrees south, panel A, and 45 degrees north, here for 1543 nanometers. So there's a good agreement between the retrieved and the true profile, so the blue and orange line, and also the corresponding transmission values and the relative residuals. That means that under the assumption made here, wavelength of at least 1543 nanometers would be necessary for the corresponding retrieval for latitudes of 45 degrees south and 45 degrees north. And in kind of the same manner, we did that for different latitudes. And consistent with our expectation along a wavelength, this would be or is required for the latitude range of and near the injection. So to summarize the last part of my talk is that the study analyzed which wavelengths, depending on the latitude, are necessary for the aerosol extinction profile retrievals in the case of continuous tropical injections of 30 teragrams sulfur per year, and consistent with expectation, longer wavelengths would be required for the latitude range of and near the injections. And the results also confirm the generally accepted idea that in the case of very high emissions, such as 30 teragrams sulfur per year, the appropriate approach would be to use longer wavelength for aerosol measurements, and therefore the results are also relevant for satellite solar occultation measurements after major volcanic eruptions. Thank you.
Thank you, Anna. Okay, we have a first question from Tyler. We have plenty of time to ask questions. Thank you for saying, oh, wow, many questions. Okay, Tyler, you're the first one.
Thanks, Anna. So going back to the first part of your presentation, it's not detectable after 1 month, either 1 or 2 teragrams. Is it then logical that it is detectable in month 2?
So you mean in the initial phase? So
Yeah.
I mean, in the first month of the initial phase, we see just 1/12 of the injected amount. So I'm not sure if we would be able to detect it in a second month, but we are currently looking at a so-called lower threshold for detectability. So, yeah, I'm not sure.
Okay, thank you.
No problem.
Andrew, go ahead.
Hi. Yeah, sorry, I just come off mute. Yeah, I just wanted to sort of ask a question slash comment, basically. It's probably not something you considered in the paper, but you might have done. In that one of my first papers that I wrote was looking at this technique to detect potential geoengineering on exoplanets, because you can use like a stellar transit method when the planet goes in front of its star, to see if there's any geoengineering being done on an exoplanet. Obviously quite far-fetched, but not something that we can necessarily discount, and might be a good way of detecting any technologically advanced alien civilizations. Is this something that you've considered during writing the paper, whether it would just be limited to terrestrial, or whether there's a way of numerically adapting your work to exoplanets?
Not yet, no. But it's an interesting idea.
Hi, Alan. You can go ahead.
Yeah, I have a couple questions. So what you're detecting is aerosols, not gas. And so in your model, how long does it take the sulfate aerosols to form from when you inject the gas?
Oh, so I'm not sure since I haven't performed the model simulations with ECAM.
Because you're talking about the first month, but most of it's going to be gas, not aerosols, so you would not expect to detect it, right?
Yeah, but we're looking at for the quasi-steady state phase, also the run is for 15 years, and for the quasi-steady state phase, we took the last 3 years and averaged them. So so we're looking at the form stratospheric aerosols, yeah.
Okay. And are there instruments in space at those long wavelengths? I know SAGE is more in the visible, but
Yeah, SAGE, the longest wavelength is 1543. I'm not sure about ACE FDS. Yeah.
so what's the minimum loading in the atmosphere in terms of teragrams of sulfur per year that you can detect?
So yeah, that's something we are currently looking at. Yeah.
Do you have any idea? I mean, can you guess?
So we looked at injections of zero point 0.1 teragram sulfur, and these are first results, but we were able to detect them after, let's say, 2 months. But there were different, like random injections, and the injection time is 10 days. But these are first results, but we were able to detect the formed aerosols after 2 months. But it's, yeah, first results.
And so for Pinatubo in 1991, the injection was about 15 to 20 teragrams of SO2, so half of that would be sulfur. And we couldn't detect it through limb scanning because in the tropics because the detector wasn't sensitive enough. There was just blocked. And I think you mentioned that earlier. So I'm wondering there must be a limit also of once you get too much, you can't see it. But that depends on the sensitivity of the satellite detector. Sage 2 was not very sensitive, but Sage 3 is much more sensitive. So how are you calibrating this based on the sensitivity of the measurement instrument?
Yeah, that's a good question. I'm not sure, but the wavelengths would be, of course, important as I shown in the last part. So we need the longer wavelength for the measurements in order to get physically yeah meaningful results above the altitude range. But the technical part, I'm not sure about.
I mean, yeah, so that's the wavelength, but the instrument can measure so many photons, and sometimes they're more sensitive than others, and so it depends on that too, right?
Yeah, that would also be a point, right? Yeah.
Thank you. Mike, you're muted.
Yeah. So thoughts about early stratospheric aerosol injection are to start up in the polar regions. Is it possible to do detection up there, at least during the sunlit season, or are the satellites just not located in the right location to get occultation up in high latitudes? Would
Yeah,
one need another satellite orbit to do that?
Yeah, so high latitudes would be actually kind of a problem. I think SAGE 3 ISS measures up to 75 degrees. So
Oh,
yeah, that would be yeah, that would be actually a problem, yeah, for high latitudes.
but could it be designed? I mean, could a different satellite orbit be used to do that? So have a polar one doing that, or just would is the geometry just not right for that?
Hmm.
I mean, the other
Yeah.
problem, of course, it's also lower elevation probable for injection, so that might make it more difficult as well.
Mm-hmm. Yeah, I'm not sure.
Thank you.
Okay, well, you had plenty of questions to answer. She also has a paper on ACP, right? About the talk you gave today. I would like to move to the next speaker, but I don't see him on. I don't think he joined.
Yeah, I just sent him another email, but yeah, he's not here, so maybe this will be a short one.
Yeah. Well,
Oh,
means that we're gonna have more time for working today.
Maybe there's somebody else that's got something prepared that they could present as everyone's here. I don't know, maybe
Wanna
someone else has got a presentation handy.
Do you have something to present, Andrew?
Oh, not me personally. I haven't got a presentation just done, but I guess somebody else is probably presenting something somewhere else at another conference or whatever, and might be able to show their PowerPoint. I mean, like, you know, it's better than nothing, right? Even if it's a presentation that some people might have seen already.
Yeah, seems a bit improbable, but
yeah.
I would like to remind people if they want to give a talk here, they can email me or Matthew. We are looking for speakers for the next month, so don't be shy. Let's just wait a few more minutes, and then I would say to end the meeting here if Francis is not showing up.
Yep, I agree.
Yeah, just 5 minutes. I'll set the timer and then I will say goodbye.
Has anyone got their cell phone for WhatsApp them?
No.
Are there any open calls that people might like to announce at the moment for conference abstracts or special issues or anything that people have got to say to the community? Well, Well, as it's all silent, I'll just mention that there's solar geoengineering updates on Substack that you can get all the news in this field on. If you subscribe to that, you get a weekly update with all the conferences and papers and stuff. Solar geoengineering updates on Substack.
Okay, I would say to end the meeting here. I don't think he's ever gonna show up. So thank you, everyone. Enjoy the rest of the day. Have a great use of these 30 minutes that you saved today. And bye.
Thank you. Bye.